Okay, so in this video, we're going to try and answer some questions related to a heating curve and really the transfer of energy still. So let's review a heating curve. There's five major um, portions on a heating curve. The first involves a solid heating up. The second involves a solid turning into a liquid, which we call melting. That will happen at the melting point, or for water that's 0 degrees Celsius. We're then going to see a liquid start heating up. The temperature will change. That liquid will then turn into a gas. We call that boiling. At water, that will happen at 100 degrees Celsius under normal conditions. And then we can heat a gas up. Now, again, the equations we're going to use, sorry, it's a little sloppy here. When you're going to heat a solid, you're going to use MC delta T. Whenever you have a temperature change, you're going to use MC delta T. Make sure you're using the specific heat for the substance we're dealing with. Remembering that ice, water, and steam or water vapor all have different specific heats. For the second stage of a heating curve, if you see that word melt, you're going to be now using the mass times HF. HF is the heat of fusion. You'll be given that value always. If you're heating a liquid, again, temperature change, you're going to do MC delta T. For boiling a liquid, you're going to do mass times heat of vaporization, HV. Again, you'll be given that value always. And then lastly, if you're heating a gas, once again, MC delta T, because we are experiencing a temperature change. Okay, let's start the practice problems. So for number one here, how much energy is required to increase the temperature? Okay. Now that I see a temperature change mentioned, I know I'm at least going to be using MC delta T. Of 100 grams of water, there's our mass, that's important, from room temperature to 22 degrees Celsius to the boiling point. Now, when I'm given these heating curve questions, I love to try and envision my heating curve. And I try and think about where I'm starting in this problem. So this one says from 22, I don't know, maybe that's around there, to the boiling point right there. It doesn't even say the word boil, it says to the boiling point. So I'm only doing one portion of the heating curve. That means I only need one calculation here. So we're going to do MC delta T. The mass of my sample was 100 grams. The specific heat of water. Down here, I did give it to you the other day. Liquid water, 4.18 joules are required to raise 1 gram of the substance 1 degree Celsius. So 4.18 joules per gram degree Celsius. I find it useful to write down all the units so that I know that the joule will be my ending unit and not a kilojoule. And on my delta T, my temperature final would be 100. My temperature initial is 22. So we get 78 degrees Celsius as my change. And you multiply all this out and we get 33,000 joules. Or it could be 33 kilojoules. Either of those could be the best answer. Let's check out number two. How much energy must be lost in order to cool 100 grams of water from the boiling point to 22 degrees Celsius? Now, this question is really just the opposite of this last one. We're just going in reverse here. We're cooling it from the boiling point to 22 degrees Celsius. Since that word lost is in there, we don't need to put a negative value. I would never talk about, I spent negative $50 yesterday. You just say you spent 50, and the word spent implies your balance going down or a net of a negative. So this would just be the same exact thing. If 33,000 joules are required to heat 100 grams of water from 22 to 100. 33,000 joules are required to be removed in order to cool it from 100 to 22. Okay, now the next question here. How much energy is required to melt 50 grams of ice? I don't even see a temperature change mentioned here. So I know that I am dealing with this process right here, this one line right here, the melting line. When I'm doing this, I'm going to be multiplying the mass times the heat of fusion. Now my mass is 50 grams, and we were given that it requires 334 joules to melt 1 gram of solid water, or what we usually call ice. You'll be given this value always. So we do 50 times 334, and we get about 16,700 joules. Okay, next question. How much energy is required to boil 50 grams of water? Again, no temperature mentioned here, so I know we are only dealing with this portion of my heating curve, the boiling portion. So we're going to do the mass times the heat of vaporization here. We have 50 grams of water. and it requires 2,250 joules to boil 1 gram of water. So we're going to do 50 times 2250. For this one, we end up with 113,000. So I think what we can notice here is that it requires a great deal more energy to turn those liquid molecules into gaseous molecules than it would to turn the solid molecules into liquid molecules. Probably has something to do with all those intermolecular forces there. Okay, last question. How much energy would be required to turn 10 grams of water at 10 degrees Celsius into steam at 110? Okay, now there's some key words here. We got to think about this heating curve now. Now 10 grams at 10 degrees Celsius would be right there on the heating curve. Steam at 110 is up here. So we need to first figure out how much energy it requires to raise the water to 100. Then we have to boil that water, and then we have to raise the temperature of that steam. So if I look at my little heating curve here, we have to add together 3 different lines. And we can't just go from 10 to 110. We need to add these 3 portions of the heating curve. So first, we have MC delta T. We have 10 grams of water. The specific heat of water is 4.18. And we're going from 10 to 100, so that's a delta T of 90 degrees Celsius. Okay, I'd calculate this one out, and we get 3,762 joules. Next, to boil that water, we're going to do mass times heat of vaporization. We have 10 grams of water again, times 2250 joules per gram. That ends up being 22,500 joules. Okay, now that we've boiled that water, now we're trying to change the temperature of the steam. When we're changing the temperature, we're going to use MC delta T. Now, we need to be careful here that this is no longer liquid water. It is steam. And if you look down here on our specific heating table, we see that water vapor has a specific heat of 2. I guess that means that it's easier to heat water vapor or steam than it is just water. So we're going to use 2.0 joules per gram degrees Celsius. And we're going from 100 degrees Celsius to 110. So my delta T is just 10 degrees Celsius. And we end up with 200 joules there. So I guess, technically this is a bad stem here. It should have given you 10.0 degrees Celsius for sig fig. So I would just add together these 3 because we need to do this and this and this. And we're saying the word and, I think that implies addition. So we add these 3 values together and we get about 26,000 joules. Okay, I'm going to make another video for the second set, and I hope this helped get you started.